Okay, welcome back. So this is homework part 2 for Carlos Co's mass transport class, or transport 2. And this is a 3-parter. So the first part, in this situation we were looking at a capillary with equal portions of water and deuterated water in a 10 centimeter capillary separated at the 5 centimeter mark. So essentially split in half. So the first portion of this question is that we're looking for the total mass flux in this situation. So, from the last video, we found that the mass diffusion flux is equal to the molar diffusion flux minus the difference of the molar mass of the component minus the mass fraction of the component multiplied by the difference in molar weights. So we kind of split off into the third part of the equation. Sorry about that. So we figured that out. And this is very key to the situation we're talking about right here. Which, if you included this last part into it and you just assumed that the mass fraction of one component was, equal to it at kind of like the final state, you don't really get anything useful. But in this situation, we're looking at the instant right at diffusion where we get rid of that barrier separating the two waters, the deuterated and the normal water. We're looking at that 0.1 second. And in this instant, we know that the mass fraction of water is, for all intents and purposes, 0. Because it's all still in its one section, just right beginning to diffuse. So it's really, really, really close to 0. We can just assume that at that point the mass fraction of water is 0. So we have something pretty nice. The mass diffusive flux equals the molar diffusive flux multiplied by the molar weight, or molar mass. But how does this get back to the total mass flux? So it should probably get there. So we know that the mass flux for a component equals the mass diffusion flux of the component minus this bulk contribution. But, as stated earlier, that mass fraction is 0, so you can just get rid of that there. And then since we know that the total mass flux of the component, or the total mass flux of the system, is just equal to the sum of the components, then we have what we want. We just have the mass flux in this situation. The total mass flux is just the mass diffusion flux of water plus the mass diffusion flux of the deuterated water, which is perfect. And all we have to do is just plug the numbers in and we're good. Since we know that deuterated water is only 2 grams heavier in terms of molar mass, and also opposite the molar diffusion flux of normal water, the total mass flux is just equal to the just normal molar diffusive flux multiplied by the difference in molecular weights. And I'm keeping this in kilograms per mole just to make this easier with units going forward. And so we get total mass flux is equal to negative 5.56 times 10 to the negative third. So that's the first part of the question. Now comes the second part of the equation, the part of the question. And that's where we have to estimate roughly the magnitude of the driving force of this diffusion in this situation. So the driving force of the water is equal to the mole fraction of the water over dz, and since we know that the driving force is equal to the sum of j to the j equals 1 of, let's see, j, and I keep saying letters, but what I mean is the molar diffusive flux of J multiplied by the mole fraction of I minus the opposite situation over the total molar concentration multiplied by the diffusivity. Seems clear-cut enough, and since this is a two-component system, we don't really have to worry about the summation of the components because of the fact that, again, it's just we have two components, and the first iteration would just be water diffusing into itself, which doesn't help us at all because it's zero. So there's no driving force of water diffusing into itself. So we really only have to worry about the water diffusing into the deuterated water. And so I'll use a subscript D to indicate deuterated water. So the mass diffusion flux of the deuterated water multiplied by the mole fraction of water, and vice versa, gets us our driving force, but not where we want it, unfortunately. So we need to figure out this all into similar terms that we can all understand, or sorry, I can understand, but hopefully you can understand when I'm done with this. So we know in this situation that the sum of the molar diffusive fluxes is zero because it's a 1-for-1 molar transfer because the molecules are very alike and it's a liquid, so we know that in this case. So the molar diffusion flux of the deuterated water is just equal to the negative molar diffusion flux of water. And then we also know, just by virtue of mole fraction, that the mole fraction of the deuterated water is just 1 minus the mole fraction of the water in the system. And so, perfectly enough, we get something that looks kind of gross. So we get that negative molar diffusion flux of water multiplied by the mole fraction of water minus 1 minus the mole fraction of water multiplied by the molar diffusion flux, or yeah, but we can cancel out a lot of terms and make this really easy, so we just, these will cancel out and we effectively get the molar diffusion flux of water, negative molar diffusion flux of water over the total molar concentration multiplied by the diffusivity. Okay, so we already have the molar diffusion flux of water. Now we have to figure out the total molar concentration, which shouldn't be too hard. Let me just make some space for myself here. So we know that the normal density of deuterated water is 1,110 kilograms per meters cubed, and water is just 1,000. And fortunately for water, we also know that the normal molar concentration of just like 1 kilogram of just water, or 1 kilogram of just water is, or sorry, not 1 kilogram of water, for 1 meter of water, how many moles of water are in that 1 cubic meter is 55,556 moles per meter cubed for water. But for deuterated water, all we have to do is just divide by the molar mass of the deuterated water. And since the molar mass of the deuterated water is only 2 grams heavier, then we know that that the normal molar concentration of deuterated water is just 55,000 moles per meter cubed. And in this situation, since we have both equal in volume amounts of water and deuterated water, we'll essentially just add these two portions up, divide it by 2, and then we get that the total molar concentration in this case is 55,530 moles per meter cubed. Perfect. Okay, so now we can do the rest of this. And so, approximately speaking, the driving force in this case is negative 2.78 moles per meter squared second divided by 55,530 moles per meter cubed multiplied by, in this case, we know that the general magnitude for the diffusivity for a liquid is 10 to the negative 9th. We get around 5 times 10 to the 3rd moles to the negative 1. So the magnitude will be probably somewhere around a high 10 to the negative 3rds to low 10 to the negative 4s. So, or 10 to the 3rd to 10 to the 4th. I think I misspoke there. I meant 10 to the 3rd to 10 to the 4th, not negative 3rd or negative 4th. So we get down to this last portion of this question, where we are tracking the mass concentration of water and deuterated water, the molar concentrations of water and deuterated water, the molar diffusivities of water and deuterated water, and then the total mass flux of the entire system over a period, over the 10 centimeters, which is what we're displaying here, and then at different intervals in time. So this is right at the initial, this is right at t equals 60 seconds or so, and this is as t gets to infinity. So, starting with the mass concentrations for both the liquids, initially they both start very concentrated on both sides of the container, but over time a gradient will form where they're still fluxing into each other, still diffusing into each other. So the mass concentration of water is 1,000 kilograms per meter cubed, and for deuterated water, it's 1,110 kilograms per meter cubed, and then it all evens off right at the end, where this higher line indicates the mass concentration of the deuterated water, and under it is the molar concentration of deuterated water, where their mass concentrations are 550 kilograms per meter cubed and 500 kilograms per meter cubed, respectively. And so we have a similar story for the molar concentrations. It's not completely analogous just due to the way of how moles convert into mass, but the molar concentration of water will start higher just because the normal molar concentration of water is higher than that of deuterated water in this case. And so we still have a similar graph as to before, where they're still diffusing into each other, but it's forming that gradient, and then once we get it to t equals infinity, the molar concentration of water is on top this time at 27,777 and so on moles per meters cubed, whereas the deuterated water is 27,000 moles per meter cubed. And then now we get to the fun part. So for the molar diffusive fluxes, you initially get this really big spike for both of the components. For the deuterated water, it's down in sort of the negative direction, and for the water, it's up in the positive direction, as we said up here. So there's that first initial spike in diffusivity, but as time goes on, the peak will slowly come back down, but the diffusion as you go across sort of the tube will slowly increase on both sides, but as time goes towards infinity, they'll fully diffuse into each other, and then you just have nothing going on. There's no diffusion whatsoever. And then for the mass flux, you have this initial spike towards the negative direction just because the deuterated water is just more massive, so it's just going to have that slight divot towards its side, or slight spike and going in the negative directions, which is closer to the water. You know what I meant? And so that just spreads out, and as that gradient as time goes on, and then as the liquids diffuse into each other, there is no mass diffusive flux, and that's where we finish.